All right, today we're going to talk about compound two-stroke diesel engines for aircraft. So what are the improvements that we can make since around 70 years has elapsed since the Napier Nomad was developed? Well, those improvements are primarily the injection system, electronic timing, and improved materials and lubricants. So for example, we can build our piston ring out of some novel material. Various alloys, including zirconium, potentially ceramics, various novel materials that we can use to increase the durability of the piston ring. Of course, a more durable piston ring means we can increase our cylinder pressure. And power is a function of cylinder pressure. The more cylinder pressure you can tolerate, the more power output you're going to make. The second improvement, this is not necessarily a technology that's developed since the Napier Nomad, but that would be using port wall valves, sleeve valves for scavenging, but overhead intake valves. So this would enable uniflow scavenging as opposed to loop scavenging, which was used on the Napier Nomad. And this would enable us to ingest significantly more air than we could by simply using the sleeve valves. Then, of course, we have free valve technology, which improves reliability. So rather than having a camshaft, we can use hydraulic free valves. It would theoretically perform better, it would enable more precise valve timing, and it would likely increase reliability, which is critical for aviation applications. Now, of course, the Napier Nomad was a turbo compound engine, which means essentially you're combining external compression with post-exhaust recuperation. Post-exhaust recuperation enables a significant increase in net power output in the order of 15% after the compression power is taken into account. So the Napier Nomad turbine developed 2,200 horsepower. The diesel engine core only developed 2,600 horsepower. Right, so we're getting almost as much power out of the exhaust turbine than we're getting from the actual diesel engine core, right? Very, very significant. Now, on the Napier Nomad, 1,800 horsepower was consumed for compression, leaving about 400 horsepower net. That accounts to about, nets us about 15% of the total power output. Okay, that's 15% of the total output, but that's out of the diesel output, about 17%, okay? So external compression is very significant for a two-stroke engine. And this is actually very intuitive, because as you imagine, two-stroke engine, in theory, would produce twice the power output of a four-stroke. But in reality, you're constrained to only about 50% more, since you're very limited in how much air you can ingest, because you have a very short window, right? Very short, narrow window in which you can ingest air. Now, of course, if you have external compression, you can open your valves, you can close your valves later, because most of your compression is provided by the external turbine. Less compression, so shorter stroke distance, is now achievable, which means the valves can shut, close later, and we're talking about overhead valves, of course, allowing a expanded window for intake. So you could theoretically ingest as much air as you would in a four-stroke, where you have a dedicated intake stroke. You could theoretically ingest not, I would say, as much as a dedicated stroke, but almost as much. because we're providing a sizable portion of our total compression externally. So you can imagine you have a two-stage centrifugal compressor can achieve an 8-to-1 pressure ratio. Diesel engine, typically anywhere from 15-to-1 to 20-to-1. We can reduce our pressure ratio about 15-to-1 for the aerodiesel. And that typically aerodiesels are going to have lower pressure ratio, lighter weight engine, less stress on the components. Now, of course, we have to understand that the way we increase the power output of an aerodiesel to be competitive with a gas turbine is by pushing cylinder pressure to the maximum possible, maximum practical level, which of course imposes a very serious challenge on lubrication and piston rings. So what's the achievable power density? Well, the Napier Nomad achieved 0.85 horsepower per pound. It's been speculated, and this is not my number, this is actually a number developed by Garrett Engine Company, which actually studied taking that Napier Nomad technology, making certain improvements to it, again, because it's significant time elapsed since that engine was developed, and potentially turning that into a practical and competitive, turning that into a viable rotorcraft power plant, which is exactly what we're interested in. Now, they speculated that they were able to achieve about 1.5 horsepower per pound. Okay, they speculated with the improvements, and this was in the 1980s. They came to a conservative estimate of 1.5 horsepower per pound. I'm using the number 1.2, which is more conservative. At 1.2, if we decide to fly 3.5 hours, let's say we have an 800 horsepower rotorcraft, which would probably be somewhere in 800 horsepower continuous power. That would be about 7,000 pounds, or a turboprop fixed-wing aircraft. Well, the brake-specific fuel consumption of the Napier Nomad was 0.35 pounds per hour. That's about what the red A03 four-stroke common rail diesel engine is, which was developed for aircraft use. I think it's based on a Audi V12. Aluminum engine block, power density about 0.7 horsepower per pound. All right, so we can see that the two-stroke is not developing anywhere near twice the power output of the four-stroke. And the reason for that is insufficient airflow. And we can solve that by providing higher external compression and overhead valves, late timing. That is going to be the major improvement we can make to the two-stroke engine. And I would predict that that would allow us to reach closer to the theoretical power output of the two-stroke as opposed to being constrained the way we currently are. Now, again, not to go off track, if we go back to our flight endurance here, we're looking at about 1,640 pounds, which includes the engine and the fuel, for 3.5 hours. Using a Pratt & Whitney 200, which the average power density is 2.44 pounds per horsepower, 2.44 horsepower per pound. That's taking all of the 11 versions of the Pratt & Whitney 200 series, averaging it out, it's 2.4. We can go to the PT642, Pratt & Whitney 200, Rolls-Royce 250, Ariel 1 and 2. These engines are all very close. The brake-specific fuel consumption is about 0.55 pounds per hour. Power density is around 2.5 horsepower per pound. If we take 0.35 pounds per hour, we're actually saving weight, believe it or not, with the diesel engine for 3.5 hours. And 3.5 hours is not, by any means, a very long endurance. If we decide to fly 5 hours, we're saving 500 pounds if we assume a power density of 1.2 horsepower per pound for the aerodiesel, or the compound diesel, whatever you want to call it. All right, so what this illustrates is the power plant is not only competitive on a weight basis, which is the most important metric, you're also reducing your fuel consumption almost in half. You're also reducing your fuel consumption by about, if we take 0.55 divided by 0.35, about 57, right? Okay, so we're reducing our fuel consumption by 43%. Of course, this results in lower operating costs. Now, the other major advantage of reciprocating engines is lower acquisition and overhaul cost. The components are simpler to manufacture, and they're just cheaper, right? Turbo shafts cost in the order of around $1,000 per horsepower certified. The projected cost of the Graphite V8 diesel engine, or actually it's not a V8, it's an opposed 8-cylinder, I think it was projected to be about $80,000. It was making about 300 horsepower. All right, let's double check that. Okay, well, so it's actually called a V8. It's actually, I guess it's a V8. 350 horsepower. 94,000. Okay. All right. So we're looking at $268 per horsepower. So it's about 1/3 the cost of a turbo shaft. And the price of the turbo shaft is based on Aerobay. That was $650,000 for a 650 horsepower Ariel 1D. Right. Okay, so what about other potential improvements that we can make to the compound diesel engine? So uniflow scavenging, overhead valves, late valve closing to enable more air to be ingested, improved high temperature lubricants, piston ring materials, common rail injection. That's about it. External compression, exhaust gas recuperation with an multi-stage axial flow turbine, which provides a 17% increase in power output and enables significantly increased airflow to basically achieve what's a hyper supercharged engine. So with that in mind, we have illustrated that compound diesel engines are competitive with turboshafts and actually offer advantages. And with that said, it would make a lot of sense to develop one for light fixed-wing aircraft and light rotorcraft. And that's what we plan on doing.